My fourth video in my module on finding the rate of change of different graphs at given points, in which we're actually going to finally define it formally as what we call the derivative. Okay, so in previous videos we found that if you were to sketch a graph and want to find its rate of change at a given point, we could sketch in a tangent line, try to approximate it. In the last video we discovered that using the secant line, its slope will approach the slope of the tangent line if we use a limit process. In this video, we're actually going to be more general about it, okay? So we say find a formula for this example. Find a formula for the slope of the graph of f of x equals x squared minus 2. Then I want to use this formula to find the slopes of the graph at these two values right here, okay? So what I want to be clear on first of all is that we have a graph here. It's just some parabola. It's been shifted down to. I suppose we could come up with a rough sketch of what this would look like. So if we were to go down to, I'm just kind of throwing this together here. It has an a value of 1 right here. So it goes up 1, right 1. It happens to go through that point. We know the basic shape of this graph, so it also goes up 1, left 1. Okay, so we say here's my graph right here. Our intent is to find the slope of this graph at 2 points, the first one being negative 3, 7. So if I were to go left 3 and up 7, let me get that a little closer here, and up 7, that'd be about right here. I want to find the slope of the graph right here. It seems that the slope would be very, very negative, or the rate of change would be negative. And also I want to find the slope of the graph right here at 1, negative 1. It'd be some positive slope that's not as drastic as the first one. So in order to do this, we are going to use our definition of the slope of the graph, which is this. We say the limit as h goes to 0. The limit as h goes to 0 of this quantity right here, f of x plus h minus f of x all over h. Okay, and we won't be able to direct substitute, but that's not going to be an issue here. The thing I want to start by mentioning though is this. This time I want to find a formula, okay, not just the slope of the graph at a given x value and plug in the x value here and here, but I want to leave x in general and let it kind of do its own thing, and then use that formula to find the slope at these 2 points. And then we're going to give this a name, okay? So let's start with this. If I'm going to find the slope of this graph, I need to know 2 things. We can do this off on the side. I need to know f of x, and I need to know f of x plus h. And the wonderful thing is we already know f of x. In this case is x squared minus 2. So we're going to keep this in our back pockets. Now we need to go find f of x plus h for this portion of our difference quotient limit. And so we have this, taking out wherever I see an x here, plugging in what we're plugging in, inserting, is this. And so when we binomial expand this, we have x plus h minus 2. I'll let you go through the FOIL on this one, but you essentially get this x squared plus 2 xh's plus h squared, and this was all minus 2 here, okay? And none of these are like terms, and that's okay, but we get this expression right here that represents our f of x plus h quantity, okay? So now we're going to go ahead and evaluate this limit. So kind of moving down here, we say the slope is equal to the limit as h goes to 0 of this f of x plus h, which is this quantity we just found here. It was x squared plus 2xh plus h squared minus 2. Okay, all of this minus now f of x, which we already know to be x squared minus 2. So we get x squared minus 2, and then this is all over h. So we're going to go ahead and simplify the top, starting with this. This is now going to be a sum. We'll go ahead and insert a minus and a plus here. But I want to notice that the 2's, they cancel out. The 2's are gone. There, that works better. And my negative x squared here and this positive x squared up top, they cancel out as well. And this is actually always kind of something that tends to happen. But what we're left with this is this, the slope of the graph is equal to this limit as h goes to 0 of this. On top we have 2xh plus h squared, and this is all over h. And you'll notice that direct substitution of your h being 0 into all of these again would produce 0 over 0 indeterminate form. But what we could do is we could use the dividing out technique, which essentially says this: if the top and the bottom share a common factor, divide it out, and the remaining expression will also share the same limit as the original expression. So now we're left with this, essentially. And our h's cancel out, and we're left with this finally. We say the limit as h approaches 0 of this expression 2x plus h. And as h approaches 0, what we get left with is this, the expression 2x plus 0, which is equal to 2x. Now this, I want to hold on to this because what we're saying is the slope of this graph is equal to 2x. This is the slope of the graph. Okay, and this actually is a formula, it's a function, and it gets a special name. We refer to it as the derivative function. We have derived this from the original function, and what this does is it tells us the slope of the graph at any given x value. So for instance, when we started this whole journey, we said, I want to find the slope of the graph at -3, 7, which is this point here. I know the x value right here. So now we can actually just take this x value, insert it into our slope formula here, and we get this. Well, the slope when x is -3 would be 2 times -3 is -6. Now I sketched this graph by hand, but I would think that this graph might just have a slope of -6 there, looking at what I'm looking at. And we also said that the rate of change at when x is 1, at 1, -1, when x is 1, we say, well, here's our slope formula. This is our derivative formula, our derivative function. We say its slope then when x is a +1 would be this. So we say the slope of my graph right here, or the rate of change of my graph right here, would be up 2 over 1, up 2 over 1 at this exact point. Okay, so that being said, it is much nicer to find this derivative formula for slope. And the reason why is because we can just evaluate the slope of this graph at any x value. And just to go to show this, I went ahead and I graphed this function here. I'll go up and grab some tangents, but these are the 2 points we're concerned with. I'll put in a tangent line here. Our first tangent line, it's kind of hard to see, but it goes down, let's see, 1, 2, 3, 4, 5, 6, and over 1. So it does indeed have a slope of -6. And if we look at this next point and throw a tangent on her, we say, all right, this one right here, looking at its slope, we suspected it would be 2. It does go up to right 1. So the slope of that is indeed 2. So this derivative formula, we're going to define it formally, but we say it is finding the slope in general at any x value. And so that would be called the derivative of x, and it is defined thusly. We say the derivative of f at x is given by this. Now I want you to notice this first of all. We denote it as f prime of x. So given f of x, which is some function, we say that this is the derivative of that function, and it represents the slope of my original function at that point. But f prime of x is equal to this limit quantity, which we're already used to, provided that it exists. So I want to try this again. I want to find the slope of this graph right here at any point x, at any x value. So we say, well, here's my f of x. We're going to find f prime of x. So we say it's the slope of my graph, which is f prime of x. This is m. And so we say that this is equal to the limit as h approaches 0 of this quantity. F of x plus h minus f of x all over h, as h gets very small. So we say we already know f of x. We need to find f of x plus h. And so I'm going to go ahead and carry that out over here where I have some space. F of x plus h means in the original function, wherever we see an x, we're going to go ahead and carry it out, and we're going to plug in x plus h instead. And so we have a binomial expansion to carry out here. So for instance, this is going to become x squared plus 2xh plus h squared on the left here. This is this quantity here. And this is minus 2x minus 2h, which is what I get when I distribute this. And so this entire quantity here, if we go ahead and combine like terms, it looks like we have x squared, that's this guy. We say 2xh minus 2x, okay? We could say, we could, I guess, leave those alone there. They're not necessarily like terms. I guess we could say they kind of are, but we'll leave them alone. And then h squared and this 2h, they don't go together either. So we could say plus 2, let's go red, 2xh minus 2x plus h squared minus 2h. So we're going to go ahead and evaluate this limit now. We say the limit as h approaches 0 of this. So the entire quantity we just found, x squared plus 2xh minus 2x plus h squared minus 2h minus our original function f of x, which is essentially 3x squared. Ooh, you know what I forgot was a 3 over here. Sorry folks. That was 3x squared minus 2x. We'll just put a 3 in front of this entire binomial expansion here. So we have 3x squared. I really apologize. This would be a 6 here, 6xh. And this would be in front of our h squared, we would have had a 3 there also. So we'll go ahead and fit this in here. We say 3x squared, 6xh. And then this would have been 3h squared here. 3. I apologize. Okay, so we're subtracting this. What I want to notice here is this. My negative 2x, this thing right here, cancels out with my, well, what would become positive 2x over here. It's gone. My negative 3x squared here is going to cancel out with my positive 3x squared in front. This is all over h. So we end up with this quantity here, the limit as h approaches 0 of this. We have left on top 6xh, this here. We also had minus 2h's and nothing left on the right, and this was all over h. And so, and this, by the way, I guess we have a plus 3h squared in here. Don't want to forget about it. It was right here. I kind of had to fit that in. But what I want to notice is this. Our dividing out technique, again, works. And it works because everything on the top has an h. So if we factor that h out, we have this. We have 3h. I'm going to move this back to the front. 3h, jump in the video here, but we'd have left over here, if we factor out an h on the top, we'd have 3h left on the inside. And these two would lose their h's. So we'd say plus 6x minus 2, and this is all over h, and as h approaches 0, we can see that these two h's divide out now. We can go ahead and direct substitute in this 0 just for this one right here. So we end up with this, 3 times, in parentheses, 0, plus 6x minus 2, which this drops out, and we're left with this. F prime of x, which is our derivative formula, it represents the slope of my graph at any point is equal to this. So this formula right here is going to allow us to find the slope of this graph at any x value. So for instance, if I wanted to find the slope of this graph at x equals 1, we would say go find f prime of 1, and this would be 6 times 1 plus 2. It would have a slope of, seems to me to be 8. So if we were to go ahead and plug this function in, it's 3x squared minus 2x. Let me get this out of here. So we have this. We have 3x squared. So 3x squared minus 2x. So here's our function. And we said find the slope of this graph when x equals 1. So I say, well, x equals 1 right here. We could say, let's drop in a tangent line to my graph right here. And as a matter of fact, I think I've done this incorrectly here. This would be a minus 2. I was like, wait a minute, it doesn't look like 8. This is a negative 2 right here. This would be a negative. So 6 minus 2, that'd seem more reasonable when I look at my picture here, but it'd be 4. And going over and looking at our graph right here, we say, is the slope of this tangent line 4? Well, it is. It's up 4 over 1. Okay, so that is how we could use the derivative in order to find a formula that will tell us the slope now given any x value that we decide to plug in. Cheers.